Okay, looks like it's going. Let's see if we're back here in a second. All right, I think we're back. Sorry about that. Let me just message that. Okay, no, something keeps beeping at me. I don't know what it is. Hopefully it'll stop. So plotting things with that matplotlib library, right, you plot an x and you plot a y. You say, here's the x, here's the y. So for what we had, I ended up using a dictionary and saying this was going to be my way of counting these values. So you could use just a regular list if you wanted and sort of use the index to represent it. I thought that was a little bit of a hassle. So I just went through and said, okay, let's go through and say for each digit here, my count is 0. And as we go find those numbers, get the string, take the first digit of the string, and then turn it back to an integer to make it fit inside the dictionary a little bit nicer. And then say, hey, my count is now +1. So it starts with an empty dictionary, 1 through 9, because range gives me 1 through 9 when I go 1 to 10. And then go through, turn them into a string, grab the first value back out. I could have done them as strings, I guess, in the dictionary. Both ways work perfectly fine. And then I plot x versus y, or x and y. And then you get a nice little plot of the first 500 Fibonacci numbers. R values, sure. And here is, we can see, very nicely fits Benford's law of a distribution here for a sequence. So, and it's weird that this works for Benford's law. That's just a whole other story here. But you can kind of imagine, like, less numbers will have a 9 as a leading digit, because as it increases, it's going to flip to the next power, and you'll have a lot of 1s, right, as we keep on going. So all sorts of fun stuff, and plotting things is always fun. So missed that from last semester if you didn't take it. It's pretty easy to get started with matplotlib, and their library or their documentation is amazing. There are like literally all sorts of things you can graph with matplotlib. And they go through all of them here. So matplotlib.org, and then their examples are just ridiculously good here. So like any sort of plots that you want to look at, I'll give you examples of how you do these pretty things. I don't even know what some of these plots are. So is that a tri-contour? Ooh, neat. So sure. So any sort of plots, right? And they'll give you all sorts of examples for these sorts of things. Basic plots are pretty easy. And this one uses the NumPy library as well, because NumPy does all sorts of good stuff too, which is really nice. And we'll just go for it. So anyway, that was matplotlib. Wrapping up on lab 2. So if you have any questions about that, let me know. We can talk more about that after. We're going to talk about recursion today. So recursion is simply defined as a function that calls itself. So a really basic, simple function that calls itself. Why something keeps beeping me? Is this beeping at me? Is it the projector? I'm trying not to touch things. My computer is like possessed. So if we have a function like countdown that takes a, I don't know, nth. Okay, so the function countdown, and we're just going to print nth, and then we're going to say if nth is greater than 0, we'll call countdown of nth minus 1. This function will call itself. Starting with any number we want, we'll print the number. If it's greater than 0, it'll recurse, call itself again, but it's changing this nth value. So technically, you don't even have to change the nth value here. If I just say nth of nth here, we're going to get a real quick infinite loop that crashes real fast. But Python lets you do it. So hey, countdown of 42. Why not? When we run this, it's going to print 42. 42 is greater than 0. It'll call it again. Eventually, it crashes here. It says, hey, your maximum recursion depth exceeded. So Python has a built-in, it will only let you have so many recursive calls at a time before it crashes. You can change it if you really want to. You probably shouldn't, though. You probably don't need to. But if we say the nth minus 1, we're going to get closer and closer and closer to making this no longer true. So this will stop the recursion. So from 42, I should get 42 down to 1, or to 0, right? And it counts down. Now, this is super basic recursion, but we've done a couple things. The first thing is we have said there's a complex problem, which is printing a number greater than 0, or printing all the numbers greater than 0, counting down. Again, not super complex, but that's the big problem. And then we said, can I simplify this problem? Can I make the problem simpler and approach something that has a known finish? In our case, the known finish is if it's not greater than 0, we want to stop. So we're taking a complex problem and we're taking it one step closer to finishing. So it's taking a complex case and making it approach what we'll call a base case. A base case is the simple, I just know the answer, done. That's the base case. No other computation has to happen. I can just solve it at a base case. So if you can take a complex problem, break it down into step by step by step, smaller and smaller and smaller, and make it approach that base case, we might be able to use recursion to solve this problem. That's a good indicator that we could use recursion to solve this problem. Not everything needs to be solved with recursion just because it can. Recursion is actually technically more expensive computational-wise and memory-wise than just a loop, right? This would, count down loop as an nth here. We can just say for value in range nth to 0, stepping by -1, print the value, right? This is a single loop. This is much easier for Python to do. Literally does the exact same thing, right? We don't need to use recursion all the time. Now, sometimes recursion makes things easier for you. So if it's just a simple loop, you're almost always better off just using the loop. But some things that are recursive in nature are harder to do what we'll call this iteratively, right? So you can solve problems iteratively or you can solve problems recursively. Anything that can be solved recursively can be solved iteratively, but not everything that has an iterative solution can be solved with recursion, because we can't always say, hey, let's break down this problem step by step by step and approach a base case. It doesn't fit always. So it's just a tool, and it's a really helpful tool because it's sort of a natural way for us to think about. You might think it's like a divide and conquer strategy. I have a big problem, I want to tackle a smaller portion of it, and tackle a smaller portion of it, and tackle a smaller portion of it until I can just solve the problem, until it's done. So a really common one here is, let's get a list of numbers here. So let's say here's some numbers, and just throw out some numbers at me, just shout them at me, and I'll add them here. 18, 22, 28, 46. I need like 10 of them, so just keep going. 94, 108, 607, 2004. You guys keep increasing your numbers. 2, 0. Okay, that's probably good enough. Now, I need this list to be sorted, so I'm going to call numbers.sort. We'll sort numbers. Remember, there's two ways of sorting things. Numbers.sort will change the numbers list. You can also say sorted of numbers. Sorted of numbers will not change numbers, but will give me a new list back out. So there's the big distinction between the two. Right? This generates a new list. This modifies the list being called on. Right? So we don't really need to at this point here, but we could say here, a copy, or sorted copy maybe, sorted copy of numbers is sorted of numbers. Sure, I like that. Again, I can't spell numbers. It's just not my day for typing. Okay, so if we have a sorted list, right, either of these will work for our approach. What we can do now is we can write a function called binary search. Binary search is a very classic example. We're going to say, hey, here's some list that we want to search, and we want a number to find. So if you tell me what number to find and you give me the sorted list, I'm going to see if it's contained in here. Now, when we did the number guessing game way back when in the first semester, and I'm assuming you probably have done that somewhere, pick a random number 1 to 100. If you want to play the smart and easy way, you pick the middle. You say 50, and then it tells you too high or too low. We've now cut the list in half because it's either too high, it's too low, or it is 50. Now I can search 1 to 50, or I can search 51 to 100. Right? I've cut it in half, so I'll do the half again. I'll say 75. Right? Now I've cut that in half, so now I have a quarter to search if I have to find it. The binary search works the same way. We're searching, starting in the middle, looking for a value, and searching high or low. So it only works on sorted lists. Right? Right? If you try and do a binary search on an unsorted list, bad stuff happens because it just won't work. Right? So we need to find the middle. Well, the problem is I don't know where my start and end points are. So I'm actually going to make another function here as a helper function. I'm going to mark it as private because I don't want the person who has to call binary search to tell me the start index and the end index. But I need to know where the start and finish were. So I can say some list, the number to find, the start index, and the end index. Okay, so the first thing we're going to do is we're just going to return our binary search of some list, the number defined. The starting index is 0, and the ending index is length of the numbers, length of numbers, minus 1. Remember, you have no index at length, so a length 10 has indexes 0 through 9. So I need the last valid index, will give me length minus 1. Now from here, okay, now you've narrowed it down. Now I know where to split the difference. Right? So if we were to kind of sketch this out instead of writing some code first, might make it make more sense. Oh, it's not plugged in is what's beeping at me here. My power. It's like, why does it say it's on battery power? That's why. Okay, that was the mystery noise. Sort of solved a problem there. Okay. So if we had some list, right, we had 0 and 2 and 8 and 32 and 64. I don't know. Those are all powers of 2 for some weird reason, but that's fine. So the initial search is going to start at index 0, index 1, 2, 3, and 4. Right? So I'm going to say, okay, binary search from 0 to 4. That's my entire range because I haven't cut anything in half yet. We say, okay, where's the middle of 0 to 4? Right? Well, 0 plus 4 divided by 2 should give me the middle. Midpoint's 2. So now I'm going to look at 2. Is 2 the number I'm trying to find? Yes, no too low, no too high. Whichever case it is, we'll say it's too low. Then we'll take, okay, it's not 2, so what's left? So then my mid plus 1 through the end. Right? Otherwise, it's mid minus 1 to the start. Right? Is the remaining chunk. And we just keep on repeating over and over and over, finding that midpoint every time. So in our code, right, we need to find the mid. So mid is going to be start index plus the end index divided by 2. And hopefully you're yelling at me right now because I've done a bad thing with order of operations. Right? You don't want n divided by 2. Right? You need start plus end divided by 2. And we want an integer result. So Python has a handy shortcut for that. Divided is integer division. We'll truncate any decimal. Right? I don't want decimal ranges. There are no indexes at 2.5. Right? So this will truncate or round down. Right? So we'll always round down to the nearest integer to make sure I'm at the half point here. Okay? And then if my sum list at the mid is equal to the number defined, we're going to return true. We found the value, right? We win. And a lot of times, actually, you even return the index. You say, hey, here's the index of where I found this thing, right? So like with lists, you can say, hey, where's the index of this location if I want to go find it? We tell you back the index. We can do that with a binary search. Return the mid. If it's not, then, right? So then, again, else here is kind of redundant because if I hit return, code after this won't run. So you don't need an else here, technically. But I'm just going to say if now some list is less than the number defined. That means the number is larger than I need to recurse. So I'm going to return binary search. The sum list stays the same. The number defined stays the same. My starting index now is mid plus 1. The ending index is still the end, right? The middle was too small. You need to find bigger, so go look at the bigger half now. Right? Take the bigger half. If I didn't do that, then again, an else is redundant, and it's not the same and it's not greater than. It must be less than. So then we do start is still start, and then end is mid minus 1. Right? So we're just cutting it in half every time. Now we missed something though. So one potential base case here is I found it. Problem solved. The complex cases that we can simplify are, hey, go check the bigger half or go check the smaller half. But what happens if it's not in here? Right? What's going to happen? Well, we need to check one more time. So we need to check first. We can say, hey, if the start index is greater than the end index, return, we'll say -1 is a pretty good indication of not found, or you could like raise an error, raise an exception. We're just going to return -1. So depending on your language, different tools will do different things. We'll say -1 not found because I don't really want to crash. Or should we can raise the exception. We can raise item not found something. Oh, what is it here? item not or index. I don't remember what it is here. Hang on, I'll come back to that. I'm going to return -1. Let's see, because I don't remember. Let's try it real quick. So we'll make a list. Numbers is 1, 2, 3. Numbers dot. Oh my goodness. Index. There we go. We want the index of say 4. Index equals numbers index of 4. What does that give us? There we go. A value error. Okay. Sure. So we could raise a value error. Value error. And raise a value error saying the number defined plus is in the list. Sure. Right. We're just kind of repeating what the Python built-in list does for us here. We're just going to return that value error. So if we've gone through and cut the difference and cut the difference and cut the difference, right, and we get down to, okay, we did 3 and 4 then, right? So 3 plus 4 divided by 2. 7 divided by 2 floor division is 3. I'm going to check index 3. If that's still too low, then I'm going to say, okay, index 4. So 4 plus 4 divided by 2 is 4. Sure. If that's still too low, right, then it means I'm going to move the starting point to 5, because mid plus 1 would be 5 to 4. Now start is greater than that. If it was less than the end, then my mid would get subtracted. My start would stay at 4, and then it would move down to 3, right? If it was too low, if I was trying to find, like, if I tried to find 50, it was greater than 32, so it would take the bigger half, which is down to just index 4 and 4, start and end. And then 50 is less than, so it would say, okay, start of 4, end of 4 minus 1 is 3. And then we'd still trip our start index is greater than the end index, not found. So we use this private function here to kind of hide some of that nasty details. You don't want them to have to tell you start at 0, end at length -1. That's a lot of work for our users, right? That good object-oriented principles here want to give them a nice, clean, abstract function to work with. Just give me the list and tell me what you want to find inside that list. I'll go find it for you. So with our sorted list then, right, we can go then call, let's say the index of, I don't know, we'll print the index of, I don't know what number, how about 94? The list is, and then we'll add in here my binary search, give it my numbers list, and 94. Right? So when this is sorted, it should be 0 to 8. So it works out pretty nice, right? So that's index 0, index 1, index 2, index 3, index 4, index 5, index 6. So it should be 6. Right? So we'll go run it and see. Oops, sorry. Yeah, 4 is not in the list. We can get rid of that code. Sorry. Yep. Well, you need to say it's a string of this. So we have to convert strings. There we go. Index of 94 is 6. So it properly counted it like we'd expect here. You know, if we wanted to give it a quick little silly test too, right? We could say, let's do this, I don't know, for value in numbers. We're going to print the index of plus a string of value plus the string in the list. Okay, this is awful here. I'm sorry. We need to do a string format. Sorry. So let's do the formatting stuff. So we can do our substitutions. So that was format the first one and format the second one. Right, dot format. So the first one was value, the second one was that. So if you haven't seen string formats before, it's a way of adding placeholders here. So these curly braces are placeholders, and then we just substitute in things that are comma separated after we call dot format. That wasn't right. There we go. Just trying to make that fit on the screen here. One more parenthesis. So it's a little easier to read the string rather than string plus something plus something plus a string plus something, right? We give it a single string value and we start stubbing in. So the first substitution, value, gets replaced here. The second substitution, binary search numbers, gets put in here. I think now I can actually get rid of that string. I think it's a little smarter now. Let's try it. And now we get, oh, sorry, that shouldn't be 94. Sorry, that should be value again. No wonder it's always telling me 6. Let me try that one more time. So the index of 0 is 0, index of 2 is 1, 18 is 2, 22 is 3, 4 is 28, right? On and on and on and on. So we see they counted the indexes properly. So our binary search seems to be working okay. We get out the correct indexes for what we'd expect here in our list. So again, binary search doesn't even have to be a recursive call. Right? You can do this iteratively. So if we define an iterative binary search, given some list and number defined, sorry, some list and, yeah, so this first one is recursive because it calls itself. It recalls binary search. So it takes the complex case and says, okay, I can make it simpler by taking half the list. Try again. Okay, take half of that list. Try again. Take half of that list. Try again. Number defined. So to do this now, I will just say start equals 0. And well, we should probably do better. Start index is 0. End index is length of some list minus 1. And while start index is less than end index. Let's keep on going. So now we need to find the mid. So mid is start minus that. If we found it here, was the number to find, there we go. We'll return the mid. Otherwise, if we haven't found it then, so if my sum list of mid is less than the number defined, that means this is greater, so I need to change start becomes mid plus 1. Right? Move the start post because number was greater than my middle. So now take the next value. Now this I need to be careful because return will stop, but a single if won't do it. So this one now I have an else because if it matched, I return and I'm done. If it was greater than, I need to move start. Otherwise, I need to move end. Mid plus 1, or mid minus 1, sorry. So if my number defined was not greater than, it was less than, I need to move the end point, not the starting point. And that's it here. Now we have an iterative binary search, and this is actually easier, right? Simpler. Less stuff has to happen. So what's really cool behind the scenes, I'm going to put this in debug mode because that's really fun. So come to the line number, put a big old breakpoint in there, and then instead of right-click run, you right-click debug. We're going to see the stack trace. So all of these function calls here. So right now, so over in this frames here, Python has to track behind the scenes what's happening. So the original start of this was main line 46. Main at line 46 said run binary search. So Python says, okay, when I come back, this is where I'm coming back to. The first thing it did then was call binary search, and we got to line 22. Binary search said, okay, call my private helper binary search. So private helper binary search now is at line 11. When this is done, we'll come back to this one here at line 22. When this one's done, we'll come back here to line 46. So all of these calls to methods and functions are put onto this stack. So we say, this is where I left off. Do this thing. When you're done, come back to where I was. If you make another function call, it just adds it to the stack. It adds it to the stack. It adds it to the stack. So as we keep on going here, so I'm actually going to use the step out here because I want to run all of the code till I hit the breakpoint again. I'll see now I'm binary searching again. I step out, I'm binary searching again. Stepping out, binary searching. Oh, I resolved one. So now there's 2 calls to binary search, and each time Python has to track what these local variables are. What was the value of the start index? What was the value of the end index? So it's saying, okay, end index was 9 and 4 for mid. In this call, it was 3 and 1 for mid. So we can see all these different calls here have to be resolved before it'll actually go and run to print out that single value here. So value of 2, let me step into. So now we're going to binary search, we'll step into again. So you see the first time, the end index is 9, the start index is 0. So if we keep on stepping, right, we get the midpoint, it's not that. So we're going to step in again now with our changed value, step into our code. Now we have a end of 3 and a start of 0. Right, the mid was 4, we took mid minus 1. So now we have 3 to 0. We keep on stepping through, right, and you can see, oh, we found it at mid. So we're done. Right? The midpoint here was 1, index of 1, we found the 2 that we're looking for. So we're done. So you can see all of these things being stacked here as we go. So all of that has to be tracked when we're using recursion. With a simple loop, there's not a copy of every variable every single time in there. So this is more efficient. Sometimes this is harder. Now there's a real classic solution. It's not worth trying to solve it myself because I don't remember how. But if we search Python tower, oh no, let's do the towers of Hanoi first. So Tower of Hanoi visualization. So I think I showed this last semester, but it's super cool. It's this legend or this puzzle, essentially. You have to move the disks from one pole to another pole, but you're not allowed to put a bigger disk on top of a smaller disk. So to do that, you do it with recursion. I think, was it this one? I forget. There's some links that are really good at this. No, I want a custom one. Oh yeah, this will even give us Python code though. That's cool. Oh, come on. Towers of Hanoi. Visualized, maybe? Visualized? There's a really good one. Is it this one? Yeah, this is the one. So towersofhanoi.info. And again, you can do all sorts of different crazy things with pegs, but 3 pegs is usually the normal one. We'll say 7 disks. And then you can show it. And this is super fun. Let's do it in like 3 times speed. It's step by step by step. And what happens is moving 7 disks is hard, but moving 6 disks is easier. Moving 6 disks is hard, but moving 5 is easier. Moving 5 is hard, but 4 is easier. Moving 4 is hard, but 3 is easier. All right, so actually, let's go down to 3 because that makes it a little bit easier here. So with 3 disks, I can't move all 3 at once, but I could move 2 disks from here to here, move the 3rd disk from here to this one, and then remove the 2 disks from here to here. So that idea, right? So I'll take, instead of moving 3, let me move the top 2, move the 3rd, and then put those 2 back on top. Well, that's still hard to move 2. So how do we do that? Well, let's move 1 to the other location. We'll move 2, and we'll put 1 back on top of it. So you just get this sort of, let's move 2, put the 1 back on top, and then move the 3rd, move the 2 back on top. It's this pattern here. So if you have more disks, right? Moving 5 is hard, but it's the same as moving 4, then moving the 5th, and then moving 4 again. Well, 4 is hard, but you can move the 4th, move 3 back on top 4. 3 is hard, right? It just keeps on building it and breaking it down here. So the Python version, let's go back. I think someone had a Python one here, is super easy. So in Python, it's this much code. Here's your Towers of Hanoi, right? We'll say, hey, if you need to move 1 disk, done. That's the base case. Moving 1 disk is solved. Easy. If it's not moving 1, well, let's move 1 less than that, and we're going to flip the target and holding location. So your goal, right, was to get from, say, tower 1 to tower 2. We're going to flip and say, okay, let's get from tower 1 to tower 3, move less than 1, move the one we want to the correct location, and then repeat the step with that. So there's a little bit of repetition here. So this is moving -1, moving the one we actually wanted to move, and then moving them back from the extra back on top. So with our 3 example, we said, okay, well, for moving 3, let's move 2 to the holding location, move the 3rd to where we want it to go, and then repeat that move of the 2 back to where I actually wanted them to go on top of me. And that's it. This is the entire function here for Towers of Hanoi. It's awesome, right? Because it's a recursive function. Trying to do this without recursion is difficult. Hey, Hector, thank you so much for donating bits. That's so cool. You keep supporting the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. I can do that in one breath now. I've had enough practice, which is awesome. We've generated more than $100 just from me like having classes on Twitch to go to this. I mean, it's only $100, but like still $100. I don't know, just for doing classes and not using Zoom. Sorry, what?
More than $0.
It is more than 0. That's true. That's exact. All right. So Towers of Hanoi. Easy to solve with recursion. This is hard to do without recursion because it's not just a simple loop. I can't just say, okay, as long as it's less, or as long as it's more than 1, go 1 less, right? It's not a simple countdown because there's this step, the original step, and then repeating that other step. So this is a little bit trickier. The other example here we want to look at, which is a really cool pattern, and this is what we're going to work on for the project, is called backtracking. The idea with backtracking here is actually relatively straightforward. So if you've ever gone to like a corn maze, or any sort of real maze, right? The idea is you have a start location and you have to get to the ending location. Right? So we're going to imagine we have a maze here. Now our maze is going to be a little bit simpler. So let's just imagine this is like a 2-dimensional list here, if you would. And let's say if here's a start and here's an end. We'll get from here to there. If there's an X, you can't walk there. right? So let's just put a couple X's around, say, hey, you can't go these locations. Why not? Here's a maze, right? So if I say, solve this maze, right? People visually can say, okay, I see the path, let's just go. The computer doesn't visualize a path. Doing that is a whole separate thing. Don't worry, you can do all sorts of fun stuff with visualization and finding paths, like by image searching, whatever, that's nonsense. We're going to go the hard way, or maybe the easy way, right? Not trying to do all sorts of fun stuff. So we'll say, okay, well, the computer then says, have I reached the end? Am I at the end yet? The end is my base case, right? When I reach the end, base case solved. Have I reached the end when I'm at start? No. Okay, well, what options do I have that could simplify this complex solution and get me maybe one step closer to the actual solution? We could go up, we could go down, we could go left, or we could go right. Okay, so we're going to, in this same order every single time, we'll try up, try down, we'll try left, and we'll try right. So from start, can I go up? Nope, can't go up. Okay, from start, can I go down? Sure. So what's happening here then, if you imagine we have this call stack here, so currently we're at solve, and we're at 0, 0, right? And we're going to try up, we're going to try down, we're going to try left, we're going to try right. We can't go up, we're going to try down. So now we're at solve. This is row 1, column 0. We're going to try up, down, left, and right. Are we at the end? No. Okay, can we go up? Why not? Yeah. Oh, okay. So if I go up, I'm going to go down, I'm going to go up, I'm going to go down, I'm going to go up, I'm going to go down, I'm going to go up, I'm down, stuck in an infinite loop. Bad thing happened. We have to be Hansel and Gretel. We have to leave a breadcrumb trail so we don't walk on our breadcrumbs. Right? So part of this process then we'll have to say, please don't go here. So we'll leave a little breadcrumb. Here, there's our little, nope, that didn't come through, right? Breadcrumb. Breadcrumb. Sure, that's a breadcrumb. I don't know, I think I'm drawing shapes or something. Okay, so now we'll say, no, we can't go up because there's a breadcrumb there. Okay, can I go down? Sure, okay, I'm going to go down. So before we go down, let's leave that breadcrumb, right? Let's be smart about it here. Breadcrumb. So now we're at solve of 2, 0. Up, down, left, and right. I can't go up because of the breadcrumb. Can I go down? Sure, okay, let's leave a breadcrumb. Breadcrumb here. So now we're at solve of 3, 0. We're going to try up, down, left, and right. Can we go up? No, there's a breadcrumb. Can we go down? Sure. Okay, now leave our breadcrumb. Now we're at solve at 4, 0. We're going to try up, down, left, and right. Can I go up? No. Can I go down? No, if we're at 4, 0 here, there's no down. Right, that's off the map. Can't go down. Can I go left? No. Can I go right? No. So this here is a dead end, right? That's the other base case. The other base case is no possible way to get closer to a solution. So we have a dead end. So I'm actually going to mark it here with, like, so let's say an E for dead end. No, E was for end here. How about a D for dead end? Is that confusing or is that okay? D for dead end. What happens is now this call comes off the call stack. We come right back to where we were. We just tried solve from 3, 0. We tried down. Can we go down? Well, no, we tried that. It didn't work. Can we go left? No. Can we go right? No. So we've reached another dead end. We're backtracking. We've tried this path. It doesn't work. We're going to come back to where we were, kind of undoing our steps as we go. So solve at 3, 0 didn't work. We found another dead end. Now we're at solve at 2, 0. We did up. We did down. We can't go left. Can we go right? Sure, let's go right. So now we're going to go, so again, our breadcrumb's already there. Sure, that's fine. But now we're going to call solve at 3, 1. We're going to try up, down, left, and right. So at 3, 1 here, this location right here, I can't go up, I can't go down, I can't go left, but I can go right. So sure, we'll leave our breadcrumb. Now we'll come to solve. Sorry, that's 2. 0, 1, 2. That should be 2. I think I went too far here. Sorry, this should be 2, 1. 2, 1. So solve at 2, 2 then says we're here. Can I go? Wow, that. Sorry, my highlighting here is getting a little funny. Can I shrink that a little bit more? We're gonna. No, don't want reading view. My goodness. Sorry, not reading view. Single page view. Single page view, please. Zoom out. Word is killing me here. Kill me, Word. And like it broke my dark mode too. That's awesome. Okay. I think you get the idea if we don't keep it going, right? So we go 2, 0 or 2, 2, and then we're gonna try up, go right, go down, go left, go down, go down. We'll try left first, that's a dead end. We'll get to the end and say, do we reach the end? Yes, we reach the end. So with backtracking, we will find a solution. Now, this path here is not the optimal solution, but because our algorithm says go up first, we tried up first instead of going right first. So we found a solution, but it's not the best one. Okay, that's another problem to solve for later. But this backtracking will find possible solutions to mazes. Same idea if you're familiar with the game Sudoku. Right? You get this 9x9 grid. You have to fit the numbers 1 through 9 in each 3x3 grid, each row in each column with no repeats. We can use a backtracking solution for Sudoku. So to do a backtracking solution, no, I just want an image, sorry. Just give me an image. Oh, sure, here's a puzzle. Right? If we have a box here, I'm going to find the first open location. So I need to do every single location. So for every row and every column, I need to, if there's not a number, put a number in it. What number should I try? Well, I'm going to try putting in a 1. If I can't put in a 1, then I'm going to try putting in a 2. If I can't put in a 2, I'll try a 3. But if it fits, I'll try it, and then I will do the next step. So that's one step closer to a possible solution of, okay, I put a 1 here. Well, 1 can't go here because there's a 1 already here. How about a 2? Sure, a 2 fits. Let's put a 2 here. Done. The next box. Okay, can a 1 go? No. Can a 2 go? No. Can a 3 go? Sure, let's put a 3 in. Next box. Oh, that one's already filled. Don't need to do it. All right, let's keep going. Can we put a 1 in? Nope, there's 1 in the row. Can we put a 2 in? Nope, there's already in the row. 3, no. 4, no. 5, no. 6, no. 7. Can we put a 7 in? There's no 7 in the row, in the box, or the column. Next one. Okay, not a 1. Oh, no, it could be a 1 because there's no 1 in that row. Next one here. Can it be a 1? No. Can it be a 2? No. 3, no. 4, no. 5, no. How about a 6? Sure, it could be a 6. All right, next box. Can it be a 1? No. Can it be a 2? No. 3, no. 4, no. 5, no. 6, no. 7, no. 8, no. How about a 9? Sure, 9 fits. Okay, next available box. Next row. Let's go here. Can it be a 1? Nope. Can it be a 2? Nope. Can it be a 3? Sure, why not a 3? Next box. Okay, can it be a 1? No. Can it be a 2? Sure, why not a 2? Next box. Can it be a 1? No. Can't be a 2. Can't be a 3. Can't be a 4. Can it be a 5? Sure, we'll put in the 5. Next box. Well, not a 1, not a 2, not a 3, not a 4, not a 5, not a 6, not a 7. How about an 8? Sure, let's put in an 8. Done. Next box. Finally, we get to a bad one. This took longer than I thought. Can't be a 1, can't be a 2, can't be a 3, can't be a 4, can't be a 5, can't be a 6, can't be a 7, can't be an 8. It must be a 9. Oops, it can't be a 9. There's already a 9 here. I can't put a number in, so I have to come back a step to where I left off. Right? This was no good. I reached a dead end. Come back to where I left off. Say 8 was no good. Take 8 out. How about a 9? Oh, can't put a 9 in. Okay, so that was no good. So go back another step. Backtrack again. 5, you can't be a 5 here. There is no solution. All right, how about a 6? Can't be a 6. Can't be a 7. Can't be an 8. Can't be a 9. Okay, that was no good. Go back even further. Number 2, you can't be a 2. That was no good. And we just keep on literally trying every single possibility until it's solved. That's backtracking. And it's actually easier than it looks. We can build one. I think we've got time to do it today. If not, we'll have time to do it on Thursday for sure. Do you want to try for it today, or do you want to call it a day because that was a lot already? I'm open to either. Yeah, we can make a Sudoku solver pretty quick. I think it usually takes about half an hour for me to do one. So might not finish today. If you want to save it for Thursday, I'm totally open to whatever you folks want to do. It's your time. Want to try it? All right, let's try it. Okay, so in Recursion here then, I'm going to make a new, yeah, let's just do a new module, a new file here. Let's do our Sudoku Solver.
Are we going to use this Backtracking for Battleship?
No, not the Battleship project. There's no recursion there. That's just classes. The next project will be Recursion. Okay, so what we're going to do then is we're going to have, let's do a class for Sudoku. Sudoku. I forget here. What? Sudoku. Okay, yeah, look at that. Spell check even helps. So we need an init method here because we want to track the board. Right? The board is going to be the two-dimensional list of all my numbers here. So I can hand this. Actually, this is my Sudoku solver here. This will solve a Sudoku for a given board here. Okay, so self.board is the board. Great, take it. Then we need self.solve, or we need a solve method. Solve. Okay, this is the recursive part here. So solve will happen iteratively here. So we're going to say for row in board, and now we need each individual location in that row. Now remember, generally a for loop here is going to be read-only, so I can't modify it. Now because it's a list, I can modify the contents of the list here. But if I say for column in row, I'm getting copies out. That's not going to work. I can't have copies here. So I'm going to say for then, this is for column index in range of 10, because we want 0 through 9. No, sorry, 9, because we get 0 through 8 is 9 total indexes. Sure. Oh, sorry, it's not board, self.board. Okay? So now, if the location already had a value, we just keep on moving. If it didn't have a value, we're going to try putting numbers in. So we'll say, hey, if, we'll say the row at the column index does not equal an empty space. If it's not empty, if it is empty, then we want to try and place something here, if we're empty. This is going to be a little bit funny because we're going to have to use characters, not numbers, but that's okay. It should be perfectly fine, because if it was a two-dimensional list of numbers, then blank is not a number. It doesn't really fit very well. So we'll just use like the quote one character, not the one integer. That should be perfectly fine. So if it's empty, then we say, okay, let's try. So we're going to say for, this is number in range 9. I'm sorry, in range 1 to 10. I want numbers 1 through 9 here. We need to see if it fits. Okay, so essentially what we're going to do here is we're going to say if self.canPlace. Now, this is actually tricky to tell if I can place it or not because I don't know what row index I'm in. So trying to use the row like this is not going to work out very well. So I actually want the row index in range 9 as well. And then it's my board, self.board, at the range row index at the column index. Now, because to figure out if I can place a number, I need the row index and I need the column index. I can't just say, hey, here's the row I'm in, because it doesn't know which row that actually is. Okay, so if we can place with the number at the row index at the column index. If we can place it, then I'm going to take my self.board at row index and column index and set it to be equal to the string version of the number. Right, because again, we wanted to use strings instead of integers. I think that'll make life easier. Maybe not. Let's leave them as numbers here. But blanks then, Python will let you have two different types in lists. It'll just be a little funky, but it should be fine. We'll say, let's place the number. Okay? Once I've placed the number here, right, I need to recurse. So I call self.solve. That's it. Solve will go find the next location to place a number. Now, what we haven't done yet is we haven't checked to see if we reached the base case of it's actually solved. Right? If we're actually solved, we should stop. So we can check real quick. So if self.is solved, and really this is if, I don't know, how about unsolved here? So if it's unsolved, we'll keep on going. Right? As soon as we call solve, if we are solved, stop. We don't need to do anything else. Okay? Well, now we have to figure out how we can place a number and how we can actually figure out if we're solved or not. Let me shrink that back down. That was really large. Okay? Well, so is solved is pretty easy, or is unsolved. If there's an open space, we're unsolved. Right? So is unsolved here. We're going to say for row in the board, if a space is in the row, return true. We're unsolved. Self.board, sorry. So for every row in the board, again, a read-only loop here is fine. We don't need the indexes here. There's nothing wrong with using indexes, but this is probably a little faster here. Say, if I found a space, we are unsolved, return a true. If we've gone through every single row, we haven't returned a true, we can return false. We are false unsolved. Not unsolved means yes solved. I know it's a little weird with these true-false things here, but hopefully this works out nice. And again, either way is perfectly fine, just whatever you prefer here. Okay, so that was unsolved. That was it. Now, how do we know if we can place a number? So we're going to define can place given a number, a row index, and a column index. Now this one's a little trickier here. So I'm going to break this up into a couple steps. We're going to return self dot can place in row, given the number and the row index. I don't think I need the column index. We'll do that, and self dot can place in column, given the number. And now this one we need just the column index, right? So I can check every row at that column, right? And come on, type for me. And so if you go down multiple lines, sometimes you need this backslash because Python's annoying. Other times it's fine. It's super weird. Self dot can place in 3 by 3 for the number, the row index, and the column index. That 3 by 3 meaning this particular grid here. So like this is the 3 by 3, the top left. This is the center 3 by 3. This is the bottom right 3 by 3 spot. This one's the hardest one, but we'll get to it. Okay, don't worry, we'll get to it. So this is breaking down a big problem into smaller problems. So if you can place it in the row and the column and the 3 by 3, good, we're good to go. We can return all that. Okay. So then we need to figure out, well, how do we do those ones, right? So let's go up and we'll write another function. So we'll define can place in row, given the number and the row index. Row index. Okay. So to do that, we need to know if this number is in the row or not. So we're going to return the self.board at the row index, right? So we're going to check that row. We're going to see if the number is in that row index. Then you can't do that. So we're going to say not in. If the number is not in that row, then you can place it true. If it is in the row, then this will be false. We'll say, no, you can't place in the row. Again, a little bit weird with the nots and these, like, this is the opposite, but we're asking if you can put it in the row. We're saying, okay, if it's not in the row, you can. Okay? And then define a can place in column, given the number and the column index. Column index. Now, this one, we have to check every row at that column index. I'm going to say for row in self.board, self.board, if the number is in the row, oh, I'm sorry, no, if the number is at row column index, number is equal to the row at the column index, return false. So for every row in the board, check that existing column. If that number is already there in one of those spaces in that column, you can't put it there. Right? If I've checked every column, or if I've checked that column in every row, and I haven't returned a false, I can say, yes, it's okay to put it here. So it's going to say, okay, at row 0, check column 5. Is that number there? No, okay, at row 1, column 5, is that number there? At row 2, column 5. At row 3, column 5. It's going to work its way down through the columns here, this direction. Cool, so we got that one, and then the last one is the hard one. It says can place in, I should just copy paste this 3 by 3, given the number, the row index, and the column index. Column index. So this one takes a little bit of thinking here, right? I've done this before, so it's okay. If this takes longer to puzzle out, that's okay. But essentially what we have is we have a 3 by 3 of grids. Right, let me see, can I just do a new document? Maybe will this work? So if I have the large grid here, 1, 2, 3, 4, 5, 6, 7, 8, sure, we'll call that good. And then 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's not the prettiest. But each one of these 3 by 3s then here, right, that's a 3 by 3. I have just a block here, I have a block here, I have a block here, a block here, block here, block here, 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 and here, right? So each one of those then becomes one of these 3 by 3 grids. Each one of those 3 by 3 grids then, if I know what the start location is, I can then check 3 rows or 3 columns out and 3 rows down from the corner. So I need to identify what is the corner location here. of each of these, right? So for rows 0, 1, and 2, the starting location is 0, right? For rows 3, 4, and 5, the starting row should be 1. Oh, I'm sorry, should be 3, right? Because I want to start at this 3 here. For rows 6, 7, and 8, I want to start at 6, right? So can we find some kind of arithmetic that will translate these numbers into the starting location? Right? Turns out it is the row floor divided by 3 times 3. Right? So for row 0, 1, and 2, divided by 3 integer division gives me 0. 0 times 3 is still 0. For 3, 4, and 5, floor divided by 3 will give me 1. 1 times 3 is 3. 6, 7, 8, floor divided by 3 gives me 2. 2 times 3 is 6. Okay, I've done this before, don't worry. But that's the arithmetic here. That gives me the starting corner. Okay, so I need to find the starting row is my row index, floor divided by 3 times 3. Starting column is going to be my column index, floor divided by 3 times 3. Okay, that will give me the top corner of which of those 3 by 3 grids it's in. Right? Taking the row and the column, right, will give me these top corners that I want for each of those little grids, for any row and column index. Right? Do we believe the math? Okay. It should work. Now from there, I need to check 3 rows and 3 columns. So for, I want row index in range from the starting row to the starting row, to the starting row plus 3, row. So this will be my row indexes I need to check. Starting here, going out 3. And then for column index in the range in the starting column to the starting column plus 3. Go out 3 columns. Right, this will give me the 3 by 3 row and column indexes that I need from any starting location. Right, find the top corner and then give me all 3 rows, all 3 columns. It will say if the self.board at the row index at the column index equals the number, return false. We have a duplicate. You can't go here. If we've checked all 9 of those locations in your 3 by 3 and we haven't told you false, yes, it's okay to put it in this 3 by 3. Will return true, right? And then if you can place a number is if you can place it in the row, in the column, and it's 3 by 3. That's it. So the last thing we have to do is how do we turn this board into a string? So it's really common to override this string representation here. So under string, or str for string, is how do I turn my class into a string? So I can say, hey, print this, print my solver. Just makes it look a little easier here. So we're going to print the board. So we're going to say we want for row in board, self.board. So we're going to have actually I think we can do it in a single line, but this is fine. This is our result is here. We're just going to take the result and we'll add to it the row. Right, probably as a string, right? String of the row. And add them all together here. And then at the end of that, then we also want to add in that new line character, a /n here. So I think the easier way here, I think we say return /n dot join. We want a string of the row or row in self.board. I think this is the shorthand notation. We'll say use a new line to join together everything for every row on the board given a string of that row. This is that list comprehension, I think is the term for it here. It's funky, don't worry about it, but it's essentially the same thing. So it should be the same thing here to return the result. And I'll leave that other comment about it. If this makes more sense, fine. I could care less what you use. The book, or the author loves doing this stuff, and it drives me nuts, because honestly, it's a little hard to follow. But you'll see this a lot because people like writing 1 line of code rather than 4 lines of code. Sure, I mean, whatever. You get the same result. So now we should be able to make a Sudoku solver. So if we make a Sudoku solver, so here's my solver is a Sudoku solver. Now the problem is I need to build out that maze to give it, right? So I need a board is a two-dimensional list of lists here, right? So then this needs a bunch of spaces for everything that is an empty location. We could give it, so that's 4, 5, 6, 7, 8, and 9, right? And we need 9 of these here. 2, 3, 4, 5, 6, 7, 8, 9. I'm going to tab all those in one. Now we need to actually go plug them in, right? So can we reset? Clear. Yes, clear the puzzle. All right, so we had 5, 4, 1, 7, 8. So we had a 5. Now we need to use numeric values here. So this was the problem. Instead of using strings, it's probably fine. But that's so 5, 4, 1, 7, and then 8. Right? I think that lines up. So I think I want to make these a little bit bigger here. Make these line up a little nicer here. Okay, just to make it a little easier on me, I'm going to add a couple extra spaces. And then we had 8, 6, 9, 5 over here. So 8, 6, 9, and 5. Oops, other direction. Okay, and then we had 4, 7, 1, 4, 7, and then I think the 1 was here, right? It was over 1. 4, 7. Oh, nope. So 7 was down here. Sorry. 7. This is the slow part here, building this out. Sorry. Actually, too many? I think we're okay. All right, and then we had 7, 9, 3. The next one. So we had a 7. Oh my goodness, I'm losing it out here. Can we just pop this over here? There we go. Let's do that. Pop this one over here. The windows left and right will snap your screens. It's amazing. Oh, it's a little bit too large though. Let's go a little more. Come on. Okay, there we go. You see it all now? Any more? Oh, that's as much as it gives. That's fine. So 7, and then this was a 9, and then a 3, and then a 1. And then a 9, and then a 7, and then a 3, and then a 4. Okay, and then we had an 8, and then a 3, and then there was a 6 over here, and then there was a 9 over here. That's probably enough, right? What do you think? That's probably enough. I mean, we're going to find a solution anyway, so we'll call that happy. Oops. All right, so pretty much lined up. So Sudoku solver given the board, and we'll say solver dot solve, and then we'll print the solver. We make that max. We'll run it. Uh-oh. Oh, I think I had some, that was not an empty string, so that probably screwed it up somewhere. Yeah, if it's an empty string, that's going to screw it up. Let's try one more time with a proper board. Oh, hang on, run. Let's see. Nope, still missing a couple here. Why is it missing a couple? That's interesting. What are we doing here? If it's blank, we'll try and solve it. For numbers in range, if we can place. So we did not do a very good job of undoing, right? If we called solve and we couldn't place, we never really undid that next step, right? So we said, okay, let's put the number. Remember, we had to go and erase the numbers if we got too far and it was bad. We never erased the number. So if solve comes back, so when solve is done, right, we're going to step, so we're going to have 81 calls to solve, right? Well, almost 81, right? Minus the couple that were filled in, because those ones get skipped. But almost 81 calls. When all of those are done, and solve is done, it goes back to the 80th, and then the 79th, and the 78th, and the 76th, and the 71st, and on and on and on and on. I'm going to say, hey, if self.isUnsolved, then I want to take my board at row and column index, put it back to a blank. Right? I want to undo this step. So this is the undo, because it was a dead end. Right? When we said, hey, take the breadcrumb out or put a dead end in here because I want to not step on it again, that's my step. Right? So we're undoing because it was bad. Now, there are no dead ends in Sudoku. You get stuck, you have to erase it, but something will go there eventually. Where with our maze, like, that path is dead, don't ever go there again. It's a little bit different, but the idea is the same thing here. Let's give this a shot. Uh-oh, are we stuck? No, that should be, if we're unsolved, put it back here. So, okay, so we're stuck in an infinite loop. Yep. What were we doing here? Oh, goodness. Solved a bunch of times. Line 27. If the number's not in, yeah, I was checking if we could place. So what happened? What did we do wrong here? Oh, yeah, that's something quick. We got 2 minutes left. We gotta. It's almost there. If it's unsolved, make it blank. Number, if we can place it. So if we can't place it, we skip it. We go to the next one. Go to the next one. Go to the next one. If we do place it, solve, recurse, go back, empty. Okay, let's cheat a little bit here and see what's happening. So every time we call solve, we'll just call print self. And then we're also going to print a new line. Just print an empty new line here. So we should be able to see our steps here, see where we're getting stuck. Okay, I'll give it a stop. So that was all the different attempts it did right away. So the first time I put a 2 in, because there was a 1 in the grid, looks good. I put a 3 in, put a 7, 8, found 6. Is that valid? Yeah, because that's the next grid over. But so it doesn't line up quite right because these aren't all strings. Maybe we should do this all as strings. That'll look a little prettier here. Maybe that's why. So I just need, it is a string of the number. I think that's the only place I have to change it, right? No, because then all the numbers need to be strings. Let's do this. Let's say number equals a string of number. Then it's going to be used as a string everywhere. It should be fine. Give that a quick run. Did it still not line up right? They're all strings now, but it's not lining up. Oh, because now my board isn't a string. All right, folks, maybe we'll have to finish this up after, because now I need all these to be strings. That's annoying. String 1, string 7. I just wanted it to line up prettier, make it a little easier to see. 5. All right, how about we pick this up? We'll finish it on Thursday. So it should just be one more little fix here. And you don't have to sit here while I type all this again, because that was boring. Wait, not a 9. What was that? A 5. You want to see it, right? You want to see it through? 5, quote, quote. I think I can just auto-format this after. Quote, 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 quote. Quote, 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 quote. Oh, give me 2. Oh, this one here. Code. Where's my format? My goodness. Auto format. Reformat code. Control Alt L. There we go. There, it lines it up. Control Alt L. Handy shortcut. Let's try it. We're getting close here. So where's it having trouble? So it's got, yeah, it all lines up now. It's a lot easier to see. The gap here. Did it ever put one in there? up to the top. So it puts in 1, 2, 3, 4, 5, 6. Okay, so we got one row in. Go here. 8. Never put something in after that 8. But it starts filling in down below. That's crazy. Did we... why did it not do that? So there was this call, and then we had a blank there. So it skipped that one and put a 6 in. 0, 1, 2, 3, 4, 5, 6, 7, 8. Range 9 and 9. What did I do wrong? Where is it? Let's see. Sorry, we can add more print commands here. It's, debugging is a little bit tricky because you have to like get to a certain value. That can be really slow. So sometimes prints are a little easier. If I can place, so something must be wrong if I can place then, right? Because it's not letting me place something, but it's continuing on. Because I should be able to, if I can't put the number in, it should undo and come back to my last solve. Why did it skip it? What's the number? Row and column index, right? I've got the right numbers here, row and column. Actually, the can place is checking that already, right? Oh, no, okay, so my can places are, is this right? So if I found the number, it's false. If I found the number, it's false. This is if it's not, and if I haven't found the number, it's true. It should be fine. This number's not in there. What is it here? Numbers 1 through 9. Let's also print placing that number, row index, column index. Give that a run. We're getting stuck here. Placing a 3 at 8, 6, 5 at 8, 8, 8, 6, 7. Never gets to that one. Super curious now. So it places a 2 at 2, okay, too far, 4 at 2, 3, 6 at 2, 0, and 8 at 1, 7. So it did that one, and it never got to place a 6 here. So shouldn't have been able to. So a 1, no, 2, no, 3, no, 4, no, 5, no, 6, no, 7, no, 8, no, 9 was no. So it should have undone. It should have gone back and tried the next one. But it never went back and tried 8 was no good. It just kept on going. So what am I missing here? So if for the row and column, we're going to try placing every number. If we can place it in recurse. If it's unsolved, undo. Why didn't it undo? All right, I'm going to cheat here again. This is awful, and I feel bad about it here, but that's okay. I'm going to say if in here, if row index is equal to 1, and row column index is equal to 7. Right. Stop. Put a breakpoint here. This is my cheating. So this way we'll get to this debug point. Here we go. So we got here. So we got our board. We're at row 1, column 7. Right, so this is the correct location. We're going to step. It is currently blank, so we're going to try all the different numbers. Right, so we're currently trying number 1. Can't place number 1. Let's try number 2. Can't place number 2. Can't place number 3. Keep on going. Numbers 4. Numbers 5. I think it gets to 8, right? 8 was good. Can't place a 7. We get to 8. We can place an 8, so we're going to place the 8. Okay, we're going to place the 8. We're going to set it here, and then we're going to recurse to solve. So I'm going to step in. So we're going to print the board. So now we're going to find the next available location here, which should be row 1, column. So I'm going to step out again, and it's going to keep running. So now we are at row 1, column 7 again. Can't do it, so now let's go to the next column. So we're now 1, 8. This is where we want it to be. This is where I should have stopped, was 1, 8, sorry. So if it's empty, it should be empty. Now we're going to try every number. Let's look at all the numbers here. So it should be none of them fit, we said, right? So numbers 1 through 9 don't fit. 2, 3 doesn't fit. 4 doesn't fit. 5 doesn't fit. 6 doesn't, 7 doesn't fit. 8 doesn't fit. 9 doesn't fit. So none of those worked. So now we go check. Oh, we're going back to the very next column before we stop. Okay, that was my mistake. So this loop is wrong. So it goes to the next column before it undoes here. So this has to happen. Okay, this was the wrong thing to do here. All right, I'm sorry. So yeah, that was the bad. So I was moving to the next location even if I couldn't place something. So this is no good. Let's do, we need a, how about a self dot current row and a self dot current column index. Row index. We're going to start those off at 0, 0. So now, instead of going through all of those, right, we need to, is that it? We have to change the row and column that we're working on, because these two loops are bad. We want to try them all eventually, but not in this particular order. So let's do this. So, okay, if we're unsolved, if self.row index and oh, we don't even need our stop here, right? Self.row index and self.column index is good. Okay, so this is nice. We don't even have to change. We don't even have to pass those then too, but that's okay. We have to change too many things. Self.row, self.column. Oh, that was my debug line. I can get rid of that one too. Self.row, self.column, and self.row, self.column. So when we go to solve them, we need to go to the next location, right? So we need to be changing these. So we're going to place it, and then we're going to change them. So we're going to say if, so we'll take self.column index. Oh, shoot, are there current? I named current column index. That was wrong. Let's say column index, row index. Column index, because now those are all proper, right? Oh, I didn't even use the underscores. That's fine. Forget it. So self.column index, let's take plus equals 1, and then if self.column index is greater than 8, right? We'll take self.column index, reset it to 0, and take self.row index plus equals 1. Add a row, right, to it, if we're unsolved. And then we want to check another then if unsolved. If we have a space, or we can, I guess, I don't know, we can check it in here too, but that's probably ugly. We'll say if self.column index or row index is greater than 8, and then 8, just break or something. We're just done. We'll just print self, right? Because then we got to the last row. Give that a shot. Oh goodness. Why did it didn't increase it right? Oh, so that when we unsolve, then if it was no good, we need to undo this step. Right? When we get back here, we're going to take self.column index -1, and if self.column index is less than 0, let's reset it to self.column index equals 8, and then self.row index -1. So try and solve. If it's unsolved, we need to change these values when we come back, so that this will properly undo that step. Let's see. Oh, come on. All right, I broke it. Look, we're so close. solve. It's unsolved. Keep going. I lost all my print statements, of course. Print self. Right. I get a bunch, but then it stops. Something must be wrong with our Ken place, because it broke it all of a sudden. So I told you at least half an hour, right? Come on. I think we're like 2 minutes over, half an hour. Let's see. Where is it failing? Increase the column index. Reset to 0. Right, 8 is the max, right? 8 was good. So if we're less than 0, reset it to 8. Row minus 1. What are we doing here? Current row index, self dot column index. So it's stuck at 0, 0, 0, 1, 0, 2. So it's stuck at 2. It undid the 6.
I don't think there's a check for the. It's not checking that there's a blank space there.
If there's
at 0, 2, there's 5 already there.
Yeah.
Yeah, but it's staying at the 0, 2.
It's never moving past it. Oh, okay, yeah, because we lost that in our shoot. Okay. I broke it. I'm sorry. We'll fix it on Thursday. Yeah, so as soon as I found an empty one, it gave up. I'm sorry, folks. That was really close. Let me end the stream, and I'll see you folks on Thursday. We'll finish it.